Hey folks, Chris McClure here. We're going to now finish up chapter 5 by taking a look at finding all the complex zeros in addition to the real zeros of a polynomial. Alright, now when we talk about a complex polynomial, we're talking about a polynomial that could possibly include coefficients that are complex. And when we talk about a complex zero of a polynomial, we're talking about a zero that could be a complex number. Now, the fundamental theorem of algebra tells us that every complex polynomial function that's of at least degree 1 is going to have at least one complex zero. And as a matter of fact, that if you have an n-degree polynomial, you can completely factor it as the product of n linear factors, okay, over the complex number system. So we're going to talk about that here in this section. Now, if you happen to know that a certain complex number is a root or a zero, and that polynomial has real coefficients, then we're guaranteed that the conjugate of that complex root is also going to be a zero. So if 2 plus 3i is a zero, then 2 minus 3i is also going to be a zero. Okay, so that will be a handy, useful guide. And also, we can now prove, even though I'll let you look in the textbook for the proof of this, that any polynomial of odd degree is guaranteed to have at least one real root. And if you're wondering why that should be true, well, just think about what the graph of x cubed looks like, or the graph of x to the 5th, or x to the 7th. And you see all the graphs of those functions always cross the x-axis somewhere. In fact, every odd polynomial, every odd degree polynomial is going to cross the x-axis somewhere. It's going to have at least one x-intercept. Now, suppose that I have a polynomial with real coefficients, and I happen to know that -2, -3i, and 2 plus 4i happen to be zeros. Well, it turns out then from the conjugate theorem that the conjugates of these two complex roots will also be roots. And the conjugate of -3i is plus 3i. And the conjugate of 2 plus 4i is 2 minus 4i. So now we have enough information to write our polynomial. It'll be x minus -2 times x minus -3i times x plus 3i times x minus quantity 2 plus 4i times x minus quantity 2 minus 4i, that sort of thing. So using that technique that we just talked about, you can say, a polynomial whose zeros are 1, 1, 4 plus i will also have a root of 4 minus i, and then you can go ahead and write that factorization like this, and then multiply all those factors together like you see here. I'm just giving you the Cliff Notes version of it. And so this polynomial right here is guaranteed to have these three roots. We're told that we wanted a polynomial with real coefficients, so that's why 4 minus i right there was a fourth root. And then the a right here is just some number, some real number. It doesn't matter what a is, A could be a million, A could be square root of 2, A could be -3, whatever. And you'll still have 1 and 4 plus I and 4 minus I as your roots. So the question here is, does it matter what A is in relation to what the roots are? And the answer is no. All right, moving along here. Find the complex roots of a polynomial function. So how do you do that? So here's an example. We'll go through all the steps. First, finding the real roots, and then factorizing to find the complex roots from your quadratic factors. Now, let's start off with this fourth degree polynomial. And then we can go through and find the potential rational zeros from the rational roots theorem. And then we go through, like we did from section 5.5, and start, testing each one of those to see if it produces a zero remainder using synthetic division or the remainder theorem. But it turns out that after you've gotten past the 1 and the -1, and then you get to the 2, that the result of the synthetic division gives you a remainder of 0. Whereas if you had tried the 1 and the -1, that maybe those weren't successful. That's why you tried 2. I'm not sure, whatever. But we know from looking at this that 2 is a root. And that x cubed plus 4x squared plus 9x plus 10 will be the quotient of that division. So then we're going to try to factor this third degree polynomial. And we go through the same process. We can start working our way through the list. And it turns out that -2, when you do the synthetic division, results in a remainder of 0. So now you have x squared plus 2x plus 5 to try to factor. And when you do that, you'll find that there aren't any rational zeros for this guy. But, of course, you can use the ideal of setting the whole thing equal to 0 and solving for x. And when you set x squared plus 2x plus 5, of course, you can use the quadratic formula. And when you do that, that works out to be -1 plus or minus 2i. So now you have formed a set of roots. This is the factorization of that polynomial over the complex number system by when you just take x minus each one of those roots. So so anyway, here's the product of those four linear factors. Yeah, and it turns out that any nth degree polynomial, just like we saw at the beginning of this presentation, any nth degree polynomial can be written as a product of n linear factors. So that's it for this section. That's it for chapter 5, and I'll probably be posting a quiz later on tonight or at the latest on Monday. Okay, I'm going to be out of town this weekend starting tomorrow, Friday. And so, but so if you send me an email, I may not get to you until I get back on Monday. Okay, so talk with you later. Bye.